All right, so let me give a brief overview of machine learning in biomedical engineering. Then we'll move on to data basics. Okay. To introduce the topics that we're going to cover in the course, I'm going to demonstrate this breast cancer data set. Did I stop sharing my screen? I don't think I did because the computer is viewing my screen, so it should be working. Okay, no worries. Okay, so in this Wisconsin breast cancer data set, we have data about some pathological samples that Dr. Wahlberg has contributed to the community. A lot of these data sets are publicly available to facilitate development of new techniques, new methods for machine learning. So this doctor has provided samples from his pathological samples for breast cancer. For each sample, he has provided 11 attributes, 11 types of information for each sample, including an ID number, which is not really something that we will use. It's not informative for us. It's just to identify which sample, which tissue that sample is coming from. The clump thickness, sort of a numerical attribute describing how thick the breast cancer was. The cell size, cell shape, how uniform they are. So some of these features are described by the doctor. They may be qualitative, they may be quantitative. In this case, they are all from a numerical scale of 1 to 10. Okay. And finally, the doctor has also provided a class label for each sample, indicating whether that cancer was benign or malignant. And the prediction problem for this data set involves, if I have a new patient, a new sample, where I know this information, where I've looked at the pathology, I've looked at the cells, I've done all these measurements, can we develop a model, can we develop a machine learning method that will tell us whether that sample, that patient has a benign or malignant cancer? Okay. So these data sets are very carefully crafted. They are human curated, they are curated by experts. Utilizing these data sets, can we develop a model that can be then applied automatically to new samples without requiring additional human intervention? Okay. So the assumption here is that these experts do a very good job of identifying the correct label. All right, so we're not going to question, at least on the onset, that this doctor may have done something wrong when they label the classes. So we'll assume that the doctor's verdict is final, it's the correct verdict. Okay. After we apply our machine learning method, we may actually later find out that for some samples, there are some questions as to whether or not they should be benign or malignant. So the machine learning method can also discover mistakes in the data set. And then the expert would then have to look at that and make adjustments to the class labels. Okay. All right. A data set can look like this. So this Wisconsin breast cancer data set is all numerical, with the IDs of the samples, followed by the 1 to 10 scale for each attribute, followed by the class label, which is at 2 or 4. Or you can look at it as an Excel file where each attribute is a column and each row is a sample. Okay. Given a training set, given such a data set, we have to first represent it. The representation will determine what type of method we can apply. Okay. Sometimes you may have to take your data and transform it to make some methods more applicable, where otherwise they would not be. Okay. And generally, you would want to extract a numerical value for each type of information that you have at your hand. Sometimes the information may already be numerical, but at some other times you may have to transform it into a numerical data. Okay. If you have, say, text, someone has written an essay, it's not numerical, right? You have to take it and convert it to numbers. We'll see some strategies for doing that. A feature space is sort of a term that we use to describe the multi-dimensional space that each sample is located in. So if you have a two-dimensional data where you only have two attributes, perimeter and area, that would be a two-dimensional feature space. And then a classifier is then developing a model that will separate one class from the other class. So this classifier is the model that we develop in our machine learning method. So a neural network will be a classifier, a support vector machine will be a classifier. Okay? And we will see different techniques for developing a classifier. A linear classifier in this case is just a line, right? Once we identify this line, we can forget about all the samples that we processed. We will only need to sort of remember the nature of this line. For any new patient sample, we can then detect whether it's above the line or below the line and make our prediction accordingly. Okay? So this line is now our model. All right? A linear model is simple, but it's not going to be able to capture complex underlying relationships that separate two classes. Okay? All right. Once we develop this model from our training set, we will then have a test object, a test sample that we will test our model with. And the test object is generally something that we left out from the training set, whose class label is known, but we did not show it to the model. Okay? We'll let the model learn this line from the part of the training set that we show it, and the part that we left out, we'll use it as a challenge to identify whether the model is correct or not for those test cases. Okay? And we will learn this concept of training and testing again later in the course. Okay? So that's developing a classification model to separate one set of samples from another. Projection relates to taking a high dimensional data and reducing the number of dimensions, and sometimes it may actually increase the number of dimensions for problems that are not linearly separable. A projection may make them separable. Okay, so you may use projection from a lower dimensional space to a higher dimensional space to make the problem easier in a way. A projection method like principal component analysis takes a high dimensional data, so each point is in high dimensions, we cannot really visualize it easily, reduces that to 2 dimensions, where these dimensions are no longer have labels on them. Okay, we'll just call this one principal component 1, principal component 2. Whereas our original space had attribute labels such as clumpiness or uniformity, some sort of names, right? That sort of you can relate to, or the biologist, the pathologist can relate to. These principal components are no longer things that you can label, although you can sort of identify what portion of it is made up of which attribute, but generally we will ignore that. Okay. But having reduced this data to 2 dimensions, we can now visualize it. So each point that was in your original dimension, original space, is now a 2-dimensional point. Okay? And you can relate these points more easily. So if 2 samples are very similar to each other in the original space, they would also show up very close to each other in a 2-dimensional space. Okay. All right. So that's going to be the topic of projection. Projection can be used as a pre-processing step before we apply the machine learning method. It can also be used as a visualization method. Okay. There are other visualization methods that sort of produce a layout that give us intuition about the problem, such as in this example, they've taken different demographic information for each country and applied a visualization method called self-organizing maps to produce this map along with its colors, and then go back to the world map, color it by the colors determined from that technique to identify sort of outliers, and now you can investigate to see what's going on with this poverty map, such as Australia has the same color as North America. You can ask questions about why, go back to your data and see what has given rise to this similarity. Okay. All right. So this was a quick overview of machine learning. Let's go into a little bit more details about the nature of the data, the types of data sets, and different classes of machine learning methods.